Welcome to Tech Packs. In today's video, we're diving into a unique project designed to enhance the efficiency of library seat management, the Library Seat Management System. This project combines multiple sensors and smart programming to track seat occupancy in real time. By monitoring both the weight on the seat and the distance to the nearest object, this system accurately determines if a seat is occupied or vacant. With the increasing need for organized and efficient space management in libraries and study areas, this system offers a practical solution. Join us as we explore how this technology ensures a more efficient and organized seating arrangement. All right, let's dive into the demonstration and see how this library seat management system works in real time. As you can see on the LCD display, all the seats are currently vacant, with weight values shown as 0 kilograms. We are now displaying the weight value in kilograms in front of each seat status on the LCD. For this demonstration, I've attached the load cell for seat 1 directly to a chair to simulate how it would function in an actual library setting. The rest of the sensors and load cells for the other seats are still set up on the board to represent the library environment. First, let's focus on seat 1. I'm going to sit down on the chair, which is connected to the load cell for seat 1. As I do this, the ultrasonic sensor will detect a distance within our threshold, confirming the presence of a person. Watch as the system detects the weight and updates the LCD to show that seat 1 is booked, along with the exact weight in kilograms. You'll also hear the buzzer, indicating the status change. Now, I'm going to stand up, removing the weight from seat 1, but I am still standing in front of ultrasonic sensor's range, maintaining that distance threshold. Notice that the system still shows seat 1 as booked, with the weight displayed as 0 kilograms. This is because, for a seat to be marked as vacant, both conditions, the weight on the load cell and the distance detected by the ultrasonic sensor, must indicate vacancy. Finally, I'll step out of the ultrasonic sensor's range, and you can see that the system now updates to show seat 1 as vacant. Next, let's move on to seat 2. For this seat, the setup is still on the board. I'll simulate a person sitting down by placing weight on the load cell and ensuring the ultrasonic sensor detects the correct distance. Just like with seat 1, the system accurately detects that seat 2 is now booked, and the LCD updates to show the seat status and weight. Now we will move to seat 3. I'm going to book seats 3. The system checks both the load cell and ultrasonic sensor conditions before updating the seat status. If both conditions indicate vacancy, the seat will be marked as vacant, along with the weight showing 0 kilograms. Otherwise, it remains booked, with the weight displayed. Now, while having seat 3 status booked, I am going to book seat 4. You can see that our system is showing both seat 3 and seat 4 booked. This method ensures that our seat management is both reliable and precise, making it perfect for environments like libraries where real-time occupancy information is essential. In the future, we can enhance this system by building a mobile app or web portal where students can monitor the status of the seats in real time. This would allow them to manage their time efficiently, even enabling them to book seats directly through the portal. I hope this demonstration gives you a clear understanding of how the system works. Let's take a look at the components involved in this project. The Arduino Uno microcontroller, which serves as the brain of the system, managing inputs from the sensors and controlling the outputs. 4 ultrasonic sensors, each responsible for detecting the presence of a person by measuring the distance to an object. 4 load cells paired with HX711 amplifiers to measure the weight on each seat. A 20x4 I2C LCD to display the status of each seat. And finally, a buzzer that provides an audio alert when the seat status changes. Welcome to the assembly section. Let's dive into the process of putting together our system, starting with the components and their connections. We'll walk through each step in detail to ensure everything is set up correctly. Step 1. Solder the 20x4 LCD with I2C converter. Begin by soldering the I2C converter onto the 20x4 LCD. The I2C converter will make it easier to connect the LCD to the Arduino with just 4 wires. Ensure that the solder joints are solid, with no cold solder joints or ridges between the pins. Step 2. Attach wires to the LCD. Now it's time to connect the 4 essential wires to the LCD. The connections are as follows. First wire VCC. Attach this to the VCC pin on the LCD. Second wire GND. Connect this to the GND pin on the LCD. Third wire SDA. This wire goes to the SDA pin. Fourth wire SCL. Finally, attach this to the SCL pin. Make sure the wires are securely connected to the respective pins and that they are long enough to reach the Arduino COM. Step 3. Connect the LCD to the Arduino. With the wires attached to the LCD, it's time to connect them to the Arduino. VCC wire. Connect this to the Arduino's VCC pin. GND wire. Connect the GND wire to the Arduino's GND pin. SDA wire. Attach this wire to the Arduino's SDA pin. SCL wire. Finally, connect this to the Arduino's SCL pin. Step 4. Solder wires to each ultrasonic sensor. Next, we'll prepare the ultrasonic sensors by soldering wires to their pins. For each sensor, solder 4 wires. First wire VCC, solder this to the VCC pin. Second wire GND, attach this to the GND pin. Third wire Echo, connect this to the Echo pin. Fourth wire Trig, finally solder this to the Trig pin. Repeat this process for each ultrasonic sensor, ensuring all solder connections are solid. Step 5. Connect the ultrasonic sensors to the Arduino. With the wires soldered to the sensors, it's time to connect them to the Arduino. VCC wires. Commonly connect all VCC wires from the sensors to the Arduino's VCC pin. GND wires. Similarly, connect all GND wires to the Arduino's GND pin. Echo wires. Connect each Echo wire to an individual digital pin on the Arduino. Trig wires. Connect each Trig wire to another individual digital pin on the Arduino. Each sensor's Echo and Trig pins should be assigned to its own unique digital pin on the Arduino to avoid conflicts. Step 6. Solder wires to the load cells via HX711 amplifiers. Now let's move on to the load cells. Each load cell will be connected through an HX711 amplifier. For each load cell, solder 4 wires to the HX711 amplifier. First wire VCC, connect this to the VCC pin on the HX711. Second wire GND, attach this to the GND pin. Third wire DOUT, solder this to the DOUT pin. Fourth wire SCK. Finally, connect this to the SCK pin. Repeat this for all 4 load cells, ensuring that each wire is securely soldered. Each HX711 amplifier should have its DOUT and SCK pins connected to separate digital pins on the Arduino for proper operation. That's all for the assembly part. Now let's move to next part. With all the components laid out, let's move on to the circuit design and schematic. Here is the detailed schematic of our project. This circuit diagram illustrates the connections between the Arduino Uno, the load cells with their HX711 amplifiers, the ultrasonic sensors, the LCD, and the buzzer. The load cells are connected to the Arduino through the HX711 amplifiers, and the ultrasonic sensors are connected to digital pins on the Arduino. The LCD is connected via I2C, making the wiring simpler. The buzzer is connected to an output pin to signal any change in seat status. Each sensor is carefully positioned to ensure accurate detection of seat occupancy. Now, let's talk about programming the microcontroller. First, we start by including the necessary libraries. We have the Arduino library, which provides basic functions for our project. We include the Liquid Crystal I2C library to control our LCD screen, where we'll be displaying seat statuses. Next, we initialize our LCD with a specific I2C address, which is 0x27 in this case. This setup allows us to control a 20x4 LCD, which means we have 20 columns and 4 rows available for displaying text. Moving on to the setup function. Here, we initialize the buzzer pin, set up the LCD display, and show an initial message indicating that the setup is in progress. Once the setup is complete, we enter the loop function, which continuously monitors the seats. In this loop, we read the weight from each load cell and the distance from each ultrasonic sensor. These readings help us determine the status of each seat. Next, we check the status of each seat using the check status function. If a seat's weight exceeds our threshold and the distance is below a certain value, we mark the seat as booked. If the opposite is true, we mark it as vacant. We then update the LCD display to show the current status of each seat using the print status function. If the seat status changes, our system triggers a buzzer using a beep function, alerting us to the change. In conclusion, the Library Seat Management System showcases the potential of sensor technology to improve space management in libraries. If you found this project interesting, please like, share, and subscribe to TechPacks for more innovative projects. Visit our website to purchase the complete package. Browse, select items, and click on Buy Now. Fill the required fields, then securely proceed to checkout, and you're ready to begin your project journey. Explore our site now to get started. Thank you for watching our video.